All right, 18 of you. Nineteen of you. Okay, shall we start? Yeah. Assalamualaikum warahmatullahi wabarakatuh. I hope everybody is doing well. Okay, so we are towards the end of the week 3. Yeah, it's already week 3, isn't it? Hmm? Sedar tak sedar dah. Minggu ketiga dah. Okay, so I've decided, right, to use Google Meet as the main platform. As for the video, I couldn't record the video and post to you. So we're going to have this class, this normal class. So we're going to have about 1 hour class, inshallah, right? And any extra or additional video will be recorded and post to you. So all attendance will be based on the Google Meet, right? Google Meet. So I have this. If I can show you for the attendance, I just use this. There is an extension here, a Google Meet attendance list. So I'm just going to use this so that I can track whoever in the class, so without calling your name, so I can get this attendance list at the end of the session. So after each sessions, there will be a file, Excel file, showing me who will turn on, will turn the class, so I can see it from this Google file. This is an example, so I can trace whoever in the class. For example, my name, I have 3 names here, 3 students to test the Google Meet attendance list. So it lists the when the student turn into the class, right? So 4:29, and how long they last in the class. Jadi ada kat sini berapa lama you are in the class. So I can trace that. So that will be based from there. We'll key in into your ARIS. Your ARIS. So I'm going to do it manually, but I'm going to trace using this Google Meet attendance list. Okay, so this first time I've used this extension. So hopefully everything's doing well. Inshallah. Okay, so before we start, I've already also share with you the today's slides, today's notes, and it's already in your shared drive, Google Drive, right? So you can download from there. And we're going to continue with lecture on the electrical drive fundamentals. This is all about fundamentals. I think you can download this is the same slide that you can find from UFuture. It's prepared by Dr. Rahimi Baru. I'm going to use that right. Okay, so let's start with the. Can you see my slide?
Yes, sir.
Yes, Prof.
Yes,
All right.
Prof.
Okay. Yeah. So if you have anything, you can raise your hand, or you can just put in your chat box. Okay, just write anything in the chat box. Okay, so start with electrical drive. All right, so we continue with the braking of electric motor. Uh, uh, just to ease of explanation, for explanation, we try to look into the DC motor drive, and to look at what's the braking of electric motor. Okay? This is not a normal. You ride a motorbike and then you brake your motor, isn't it? That's not what does it mean. eh? This is how you brake the electric motor that you apply to, for example, a hybrid car, uh, or you controlling any industrial application. So how you going to control the motor without any external mechanical braking? You have to differentiate between mechanical braking and electrical braking. So mechanical braking is just like a normal motorbike brake system. You have this what do you call it? Brake pad, isn't it? And we have a slip, the disc, the brake disc. That is something different, right? So that is a mechanical braking. Now we talk about how you're going to um, slow down the motor, or you want to prevent it from going very high, um, a reverse direction. So this is known as electric motor braking. Okay, so we start with what is electric motor? It is anything that turns electricity into motion. So this is a power flow from electric to mechanical, electrical to mechanical. So it's a power flow from electrical to mechanical. So you actually turns electricity into motion, meaning electrical energy into mechanical energy. It's called an electric motor. So how do electric motors work? All are based on electromagnetism. So we know that when charges are still, they create electric field. Normally, this is for the normal permanent magnet, isn't it? So for the magnet, we have this north and south pole. So the flux will travel from north to south, isn't it? As displayed by the figure there. And then we have this um, the theory, which is a current in a wire produces its own magnetic field. So if you have, can you see me? Do you see the slide and myself, or you just see the slide? Only the slide.
Both, Prof.
Oh, both. Okay, you can set, isn't it? Okay, right. So we use the right hand rule, isn't it, to determine the direction of the magnetic field. So you use your right hand. So you look into the current. So your thumb become the current direction. So you can predict the magnetic field. So in this case, the magnetic field is going round in that anti-clockwise, and then you have the current flow from positive to negative, right? So this is what we exploit in electric motor to create movement. And based on this theorem, then we have this as fundamentals how the electric motor works. How do electric motors work? An electric motor contains a coil of wire. So normally we wound a coil of a wire. So we turn, or we make it we wound a wire to become a coil. And sometimes it's called as a solenoid that creates a magnetic field when electricity flows through it. This is collectively known as an electromagnet. Then a current is sent through a loop of wire positioned inside this electromagnetic field. And then it turns out that when the current flows through a magnetic field, the charges feel a magnetic force, and then at 90 degrees to the directions they are moving. So to look into the orientation of the force, the field, and the current, we use this left hand. For the motor, motor operations, we have the left hand Fleming rule. I can't remember what is that. Is it a Fleming right hand rule, left hand rule? So the thumb will be your F, the force, your apa ni, jari telunjuk ni, as your field, the B, the B, the magnetic field density direction, and I, FBI. So your middle finger here shows the direction of your current. Okay, so this is what you need to use to identify it. All right, so in this case we have a coil. Let's assume we have this coil, and this coil A, B, C, D, E is connected to a battery. So when you connect into the battery, this coil will have a current flow inside it. Is it? So if you have the positive and negative, this is positive and negative. So you see that the current flow into that direction, isn't it? Right? So that will be the current flow. Okay. So to determine, so in this case, at this area here, we see that the coil here will be experienced. It will experience a force which is in which direction? Is it toward into the slide or outside of the slide? Can you tell me? Is it inside X to show that it's going inside the slide? The dot is to show that whether it is coming out of the slide. Can you predict which side that this coil will move? Anybody? Is it going into or going out of the slide? The F.
Into the slide.
Into. Okay, there is a response into the slide, isn't it? It is into. So if you apply your left hand rule, the current flow in that direction, and then you have your uh, your jari telunjuk ni, on the left, going to the right, then you see that the force is going into the slide. So you have this as a mark as X, that direction, and in the opposite coil here, you will experience force that is going out of the slide. So this is your F, the force. And because of that, then we can see that this coil will be rotating. Isn't it? It will rotate in that direction. Okay, you rotate clockwise. If you have this as an axis, you have that axis, so it will rotate in the clockwise direction. Clockwise direction. Okay, because of these magnetic forces, the field also going in inside direction. Side B feels the force into the page, D feels out of the page. These two forces together cause the loop of wire to rotate. We don't have any this C, isn't it? Because in parallel, the current flows in the parallel of the flux density, so there is no flux, there is no force will be experienced by C. Okay, next. How do electric work? Okay, when DC machines operate as a motor, input to the machine is electrical power and the output is mechanical. The armature is connected to a DC supply. The motor will develop mechanical torque and power. Distribution is used as motor than the generator. This motor can provide a wide range of accurate speed and torque control. So we have a few configurations, few connections. This is known as separately excited motor, which means the field winding separately excited is actually referred to the field winding here. It is separate from the source, the VT, the terminal voltage. It has a different power supply. There's a different power supply to give current to the field winding, to create the field, to create the magnetic field inside the motor. So this is known as separately excited motor, and we have this EA. EA is known as the back EMF. All right, so back EMF equals to EA, and the equation for EA is, if you use this KVL, this is KVL, then you can see, you can find out that EA equals to VT minus IARA, and this is motor operation. All right, because current flow into the back EMF here. You can also have this generator operation, whereby the current flows out of the positive terminal of the back EMF. Right, so now we discuss on the motor, and the current flows in the direction towards the positive terminal there, and therefore you have this equation EA equals to VT minus IA, and we also know that EA is also defined by KE flux omega M. Okay, so this is a motor constant, depends on the motor. It has its own constant depending on the winding, the size of the motor, so that gives you KE. KE, and flux is depends on this IF here, right? So flux actually proportional to IF, right? So here, this is equation of back EMF. Okay, right. So this is the first configuration, which is separately excited. Okay, then we have the self-excited. This is known as self-excited motor, which means if you look at the shunt motor here, the IF, this is your IF, which needs to generate the field, magnetic field in the motor, is actually supplied by the same terminal voltage, and this is known as a self-excited motor. Okay, this is actually a review. Self-excited motor. So for self-excited motor, you can have shunt connection, you can have series connection, and you can also have compound, which is the combination between shunt and series. It contains both, and you can also have short shunt, short compound, and long compound configuration. Right. So what's the equation involved? Of course, we have this EA equals to VT minus IARA again, and VT here is VT is this. It can also given by this equation IFRF, and you can also have VT equals to I T. No, sorry. So VT equals to IF because they are in parallel, isn't it? VT parallel with that RF, so it is IFRF. Even though this is a winding, since the current is DC, so the voltage drop only at the resistance. So IFRF, and we have this IL equals to IF plus IA. Okay? This is motor operations. Okay. Next, steady state equivalent. Let's look at the this is a normal separately excited. is a separately excited motor. Steady state equivalent circuit of armature. So just write to you this equation: Ke flux omega m. Ra is the armature resistance. For separately excited and shunt motors, it is equal to the armature winding resistance. Okay. Next. So the basic equation applicable to all DC motors are EA equals to Ke flux omega m. And we also have an extra equation here now. The torque of the motor equals to Ke flux. They are the same. Right? So voltage is due to omega m, but the torque is due to the armature current. You multiply with the same parameter here or variables here. Ke flux, this is for Ke flux. Flux is flux per pole, R is resistance, omega m is the speed of armature, Km is torque motor, and Ke is motor constant. So from the above equation, we are getting this omega m equals to Vt divided by Ke flux minus Ra over Ke flux Ia. Okay, and we can replace that torque equals to, just now we have torque m equals to Ke flux Ia. So if you replace that, then you get this equation here. All right, let's proceed. And then in case of shunt and separately excited motors with a constant field current. So if you have a constant field current, mean flux also constant. As I mentioned earlier, I depend on the IF, isn't it? So flux equals to IF, and therefore here actually there is a missing flux here. So that should be Ke flux. Can you take note? This should be Ke flux, not the K only. This should be Ke flux equals to K. Because both are constant, so you can only that the new constant, define the new constant as K. So you have Tm torque equals to K multiplied by Ia, Ea equals to K omega m, and finally you can reduce the equation to become this. All right. Right, now we look into the what is braking. The process of, so by the way, this is will be used for the speed control later on. Right, this equation will be used to look into the characteristic of the motor for you to control the to have the speed control of the motor. Okay, so what is braking? It is a process of reducing speed of any rotating machine. Of course, braking, we talk about braking, it's a process of reducing. You want to slow down the rotating machine. The term braking comes from the term brake. We know that brake is an equipment to reduce the speed of any moving or rotating equipment like vehicles, locomotive, car, motorbike. The process of applying brakes can be termed as braking. We can classify the term braking into two parts: mechanical braking and electrical braking. This is what I did mention just now. I talk about mechanical braking. This is the normal motorbike, braking system, the car braking system. You have always have this brake disc, and your brake pad, the cable, everything. So that is a mechanical braking. And now we only focus on the electrical braking. So it depends actually on the flux and torque direction. So you have to think on the motor, right? Imagine you have a motor rotating, and how are you going to slow down, or you're going to make it stop? How are you going to apply the braking? Of course, there shouldn't be any mechanical or outside or additional external system to brake your motor. You have to think of in terms of torque and flux of the motor so that you create an electrical braking to slow down the motor. So you have to think on how you're going to apply the torque or power to the motor so that it will stop or it will slow down your motor. So we will further see through the various types of braking, but the main idea behind each type of braking is the reversal of the direction of the flux. So how are you going to uh, uh, change the direction of the flux, change the rotation of the flux from clockwise to anti-clockwise, for example, from the left to right, right to left, left to right direction. So how are you going to do that in terms of electrical braking? So braking is a generic term used to describe a set of operating conditions for electric drive. It includes rapid stopping. Look at that. It can be rapid stopping. You want to make it the speed from a certain speed RPM. You want to make it a rapid stop. You want to make it zero speed, zero RPM, instantly. So it increases. That's also the braking of the electric motor. Or you want to holding the motor shaft to a specific position, for example. Eh? So instead of you want to, because it probably you have there is a slope on the and any application. So you want to stop that at any position. You want to move your motor so that it stop at any position. So that also using the braking. You want to hold something at a specific position, or you want to maintain the speed to a desired value. You want to maintain it rotates, but it maintain at the speed. Again, if you are going down the hill, you want to maintain the speed of your vehicle, your car, right? So you need to apply the braking. You need to brake. You need to apply the braking system to your car, isn't it? So that it move with a constant speed, isn't it? And finally, you want to preventing the motor from overspeeding. Again, you can think of the motor that going down the hill, isn't it? A car that going down the hill. So instead of the car will roll over speeding. So you have to apply the brake so that it will slow down the car for to go over speeding. That'll be like right. And all these aspects of braking are done electrically without any need for mechanical brake. As I mentioned just now, there's no mechanical brakes that you need to apply for the motor. And this is electric braking of the motor. During the braking process, the energy change is flow between the electric source and mechanical load. So you have to understand when this happens, there is actually an energy that travel back from mechanical to electric. So the motor now behave like it is a generator. Yeah, if you look into the motor circuits, now it becomes generator. Right? Instead of operate as a motor, it operates as a generator because of that braking. So the mechanical load, the external load or rotating mass can become the source of energy driving the machine as a generator, which pumps the energy back to the electrical supply. Compared to the mechanical braking methods, electric braking is a highly efficient and low maintenance technique. So if you apply the electric braking, is said that is a highly efficient and low maintenance technique, because if you just think about the normal mechanical braking system of a vehicle, you need to replace the brake part, brake pad, isn't it? After a few thousands a kilometer, you need to change your brake pad, isn't it? And after another 2 or 3 years, you may need to change the disc brake, isn't it? So it requires a high maintenance. So nevertheless, braking can result in stressful electrical and mechanical transients. What does it mean? The braking can actually create a high current, for example, and there's a mechanical transient as well. stressful electrical. So when you do some braking, the current could be very high that will, you put your electric components into a stressful condition. So therefore, the braking system must be designed to ensure effective and safe operation. In braking, the motor works as a generator, developing a negative torque which opposes the motion. Simple. Eh? So in braking, the motor works as a generator, so it develops a negative torque, which opposes the motion. So which means if the motion going towards down the hill, so you need to apply a negative torque that push it uphill, going the opposite direction of the downhill. So it has to be uphill, isn't it? Yeah? So there are three types of braking. The first one is known as regenerative braking. Second one could be the dynamic braking or rheostatic braking. And finally, you have the counter current braking, or also known as a plugging or reverse voltage terminal. So you just simply change the terminal voltage so that the negative torque is experienced by the motor. So again, regenerative braking. In traditional or conventional mechanical braking system, the brake pads produce friction with the brake rotors to slow or stop the vehicle. So additional friction is produced between the slope wheels and the surface of the road. This friction is what turns the car kinetic energy into heat. In most cars, it's the inevitable byproduct of braking, and there's no way you can drive a car without occasionally hitting the brakes. It's a byproduct. So if you buy a car, of course, you have a braking system there. And you need to drive a car with, of course, you're going to apply the brake all the time. But automotive engineers have given this problem a lot of thought and have come up with a kind of braking system that can recapture much of the car's kinetic energy and convert into electricity so that it can be used to recharge the car battery, as I mentioned earlier. So let's say we have this DC system whereby you have, this is your motor, and you have EA back EMF and plus minus, let's say, and then you have this armature resistance, and let's say you have these V terminals here, VT, this is RA, and the current, right? So during braking, the current actually moves in that direction, isn't it? And the current goes into that direction, which means EA is higher than VT, isn't it? So in this case, actually you are operating it as a generator. Okay, so during this braking system, it is best that you capture the energy. You capture the energy, or probably you use it to charge the battery again. So you charge the battery during this braking system. So that's why it's known as regenerative braking. So that can recapture much of the car's kinetic energy and convert it into electricity so that it can be used to recharge the car battery. Right. With the regenerative brakes, on the other hand, the system that drives the vehicle does the majority of the braking. When the driver steps on the brake pedal of an electric, or these types of brakes put the vehicle's electric motor into reverse mode. It goes into reverse mode, causing it to run backwards, slowing the car wheels. So this is how the electric car, instead of there is a mechanical braking, actually it used the motor itself, where you apply a reverse torque so that it actually work in the reverse mode. So you have to think on you have a quadrant, is it? Last class we talked about the quadrant. You have omega, the speed versus torque. Is it? Plot. This is a positive omega m torque of the motor. So you have this as a quadrant number 1, quadrant number 2, 3, 4. So this is motor. This is braking. So you have motoring. This is braking. And we also have this forward motoring. So forward braking. Here we have a reverse motoring. That's reverse braking. So we have this is omega m. And you also have torque in that direction. And then you can draw for the rest. So you have to look into the quadrant. This is known as the 4 quadrant. Right? So your motor can sometimes work on the first quadrant, or probably your motor can work, the 2 quadrants. Yeah? So, and normally it works at 2 quadrants, but some of the motor can be designed so that it work under 4 quadrants. Okay, so you can speed. You can move the motor to the right hand side, as well as you can move the motor there on the left hand side. And you can either right side or left side, or clockwise, anti-clockwise. So, and you can apply the brake if, in this during right movement or during left movement. So that actually motor that can work up to 4 quadrant. 4 quadrant. Okay. While running backwards, the motor also acts as an electric generator, producing electricity that's then fed into. This type of brake works better at certain speed than any other. In fact, the most effective in stop and go driving situation. So regenerative braking takes place whenever the speed of the motor exceeds the synchronous speed. Okay. What is the synchronous speed? Anyone want to answer what is the synchronous speed? What is this? In induction, we have S. What is the synchronous speed? Just give a guess.
The speed of the rotating magnetic field.
Great, Alif. Thank you, Alif. That's a good answer. It is the speed of the magnetic field in the motor. So the motor itself, when you talk about regenerative braking, at that particular condition, your motor, the speed of that motor actually exceeds the synchronous speed. Then you have this regenerative braking. So this braking method is called regenerative because here the motor works as generator supply itself is given power to load. You can do that. The main criteria for regenerative braking is that the rotor has to rotate at a high speed. Only then the motor will act as a generator, and the direction of current flows through the circuit and direction of torque reverses. Okay. The only disadvantage of this type of braking is that the motor has to run at super synchronous speed, which may damage the motor mechanically and electrically. It can be done at subsynchronous. Because you exceed the synchronous speed, then the motor actually experience, you can damage the motor, and therefore you can work that synchronous speed at variable frequency. So if you change this is a more on induction machine. Okay, this is actually discussed on induction machine. So you have F 50 hertz, isn't it? Normally you have 50 hertz. But if you able to have a variable frequency converter, you can change that to F equals to, so for example, 30 hertz. Or you can have 10 hertz. So therefore, your motor will not operate at high speed. Okay, so because you change your mains frequency to 10 hertz, then your omega m now uh, will be limited to a certain speed rather than you operate at 50 hertz. So your omega m could be very operate at super synchronous speed, which means higher than the synchronous speed, and that will damage the motor. Okay, let's think of this regenerative braking of DC shunt motor. So just for the example, actually this is you can refer to Sharkawi. Wait, this is actually from the Sharkawi books, the e-book. Page. There you are, 107. So if you can refer to 107 to get a more explanation, right? You can read that. So that is a Sharkawi book, page 107. So that gives a more explanation on this regenerative braking of DC shunt. So I'll try to explain the slide. Okay, so the machine is in the regenerative braking mode when the speed of the DC machine exceeds no load speed. So now let's look at the convention. Clockwise is forward motoring. So we have a convention here saying that if the motor rotates in that direction, we have a positive or forward motoring. Okay, for example, this you have the forward motoring, isn't it? Okay, so uphill direction. So in this uphill direction, of course, there is a load force, and this is obviously mechanical. Sorry, the motor force that you need to apply in the opposite direction of the load, which is come from the mass, the friction of your motor here, of your vehicle here. Okay, so your car, just put as a car here, your car, right? So there's always a force that drag in downhill, isn't it? So you need to apply in this direction. You have to operate as a motoring. You want to rotate the motor in that clockwise direction, uh, and therefore this is the motoring mode. And at this point, you see that the FL equals to FM. Sorry, there's no torque in this direction. At peak of the hill, torque is 0. Okay, right. So you also need to have your torque in that direction. Got it. Got it. Okay. However, when you go downhill directions, so you need to have a torque which is opposite to your motor here, isn't it? So that you can slow down or you want to stop. Yeah? And this happens when now your FL change, isn't it? This is where you have two conditions. Your force can go to left hand side or downhill direction or uphill direction. Okay? This is the one that changed, isn't it? During the movement of the car. So going uphill, the load force is to the downhill, and if the car goes down the hill, downhill direction, you see that the load force is actually going down the hill direction. So it is actually dragging. You can see that if you do nothing to your motor, your car here will go over speed, isn't it? You speed up, you will accelerate to a very high speed, isn't it? A very high speed. So you have to apply the torque here to oppose the movement of the motor here. Therefore, you have a negative or it calls a regenerative braking of this. And in that case, your force now has to go uphill. Force of the motor should go uphill. So this is where the condition of regenerative braking, right? And next, in the downward direction, the speed of the bus, so now it calls a bus, not a car. It can be a bus or car. So now we have a car, so let's maintain as car. So the car may exceed its no load speed and hence generate electric power that can be pumped back to the source. So during this time, you can you need to have a torque which is opposed to your movement of the motor here, and at the same time you can also have the current that generate electric back to the source. You can charge the battery during this downhill direction. Right. In the uphill direction, the DC machine acts as a motor. So uphill direction, of course, DC machine acts as a motor. The load torque in this case is opposite direction to the direction of the bus motion. This is a load torque, FL, PL. Okay, and the drive resistance in the first quadrant. Okay. This is the first quadrant. Great. So quickly, when you talk about first quadrant, you have to draw in your brain, in your mind, should have this 4 quadrants. So 1, 2, 3, 4. You have omega, you have torque here. So you are in this right quadrant. So this is the equivalent circuit. If you have a set shunt connection, it's a shunt connection. So I goes to that, the motoring. So under this condition, the back EMF EA is less than VT. So EA less than VT. Due to the voltage drop, those are much better. All right, and this is picked up, but actually one could correct this. This is actually M. Is that it? Not the load torque, but the motor torque. Because it's positive, isn't it? Okay. Figure above shows that the speed torque characteristic of a DC machine. The load torque is assumed to be directional during uphill and downhill. So the load torque is assumed to be directional during uphill. So we know that the torque there actually can be in the right direction, uphill direction, or downhill direction. Depends where the car is. So that is a bidirectional. load torque is assumed to be directional uphill. Okay, there you are again. Let's assume that operating point 1 represent Q1. The point Q1 here, quadrant 1. This is Q quadrant. Up here, when the bus reaches the peak of the hill, so when it goes up to that point, up peak of the hill, the load torque seen by the motor is 0, assuming the friction torque is 0. So when it go at the peak of the hill, torque is 0, and then it move into point 2. The position of the motor is out here where the speed is. Remember, you have omega equals to Vt K flux minus Ra K flux multiplied by E. Okay. So at this point, you have Ia is 0, so this is 0 as well. Okay, you have V over Vt over K flux. Because the load torque at the top of the hill is 0, the armature current must also be 0. So TL over K flux equals to 0. Since the current is 0, the voltage drop across the armature resistance is also 0, and therefore Vt equals to Ea. These operating points represent operating point at point 2, which is the no load operating point of this machine. Now, assume that the electric bus is traveling in the downhill direction. So now let's focus on this. Good. The load torque in the downhill motion is reverse. So the load torque now reverse. And in the same direction of the speed. Look at that. Same direction of the speed. So you have a torque in that direction, torque L. When you also have omega n in that direction as well. They're moving in the same direction. Okay, so that is actually that point here. So that's why I correct this should be m, not l, because you are already a negative, isn't it? This torque. So here is a y, so this is negative torque. This is positive torque. Right, so that shouldn't be top. It shouldn't be a low top. Would be the motor, and then the top of the motor here, point here. So your motor top actually traveling in the reverse direction. So your PM should be in that direction. It's negative, isn't it? It's negative. TM, TL is positive, TM is negative. So that define quadrant 2. Note the motor speed will not change direction and the motor moves to operating. The load torque changes direction while the field current remains in its original. So in terms of circuit, this is what you're going to see. Right? You have the field still in that direction. Current goes back to the terminal, and therefore you have armature current is reverse in these operations. So you have Ia3 equals to load torque divided by K omega flux, K flux. And we have this Ia equals to Ia3 minus If. Okay, so the motor is now generating electric power and delivering to the source. So in this quadrant 2, second quadrant, the current goes back to the terminal. Actually, you can recapture this and you charge back the battery. Right. This is equation. So now the speed and current of the machine at point 3 can be represented by the following equation. This is a motor equation. If I can change, if I can write into the equation, so you have so motor operation should be in that way. Motor. Okay, so you have what? So you have first is EA plus minus in motoring mode. You have minus VT plus, let's say this is IARA plus EA0. Therefore, you have minus VT plus IARA plus K flux 0, and you can have omega n equals to VT minus IA divided by, here you use a K flux again, not consistent, not very consistent. That is K flux divided by flux, right? And we know that top equals to K flux IA. So you can replace that and it becomes VT now this equation. It's correct, isn't it? We have this that direction. This is actually from that equation here. You can find that IA VT minus EA. So note that TL3 is negative in generating mode. In generating mode, the braking, regenerative braking mode, which is Q2, the top here is negative. So it changed the positive here. Or you can simply actually, you can start from KVL from, doing the KVL from the circuit here. So your current now in that direction. You can try to do that KVL, take that KVL, and you're going to have this equation. You're going to have this equation. Positive. Instead of negative, you have a positive equation. So IA equals to VT minus. Right? So that's the equation for regenerative. So this here we have a motoring. Right. Quadrant 2. Quadrant. Okay. Next, since I is negative, so EA3 must be larger than VT. The motor is operating as a generator. And this is back EMF during regenerative braking. So that is the point where you have EA equals to VT. So this is where you have point number 2. At the tip of the motor, you have EA equals to VT because IA is 0. This point, you have IA equals to 0. So figure above shows the motor speed versus EA for all 3 operating points. The machine acts as a motor when EA equals VT, and the machine is generator when EA greater than VT. Okay, so this you can also again refer to Sharkawi if you like. Sharkawi books. Right, there's a page somewhere after 107 already. Yeah, page. Okay, page 107 and above. You can see this regenerative braking second quadrant. So this is first quadrant uphill, and this is the second quadrant downhill, whereby you see that your omega is the same direction with the load torque, but for the TM, the motor torque is opposing the load torque as well as the speed of the rotating direction of your motor. So that is under the downhill, uphill. And here we have a regenerative braking. Okay, I think that's it for today. All right, you can try to do the samples to calculate what's the no load speed, motor. You can try that, right? So no worries for attendance. So we have about 22 students. So I can end this session. Then there will be 22 names. Will be so there are 3 students missing. 3 students missing. Right. So no worries. I will communicate with you through WhatsApp. Okay. And again, if you have any questions, just throw the question through WhatsApp group, so that I can try to answer through that, so that everyone can benefit from the questions. Okay, right. So we stop this slide, and then we're going to continue next week. Have a good weekend. Is there any questions?
No, Prof.
No, sir.
No, sir.
Okay, great. Okay, so enjoy your weekend. Do some, physical activity. Just do not jangan tidur je. Tidur je weekend tak boleh. Go for, play football, running, instead of PUBG je. Okay, do some physical activity. All right. Okay. So anything, you just WhatsApp through the groups, and inshallah. And today session, the recording session will be sent to you, inshallah. All right. Okay. Assalamualaikum warahmatullahi wabarakatuh, and have a good weekend. Bye.
Thank you, sir.
Thank you, sir.
Thank
you, bro.
Okay.
Thanks,
Thank you.
Thank you, sir.
All right.